In this video, we will talk about stack defense. Before we talk about stack defense, let's first recap what we have learned for Stack Overflow exploit. We can just conclude exploit as 4 steps. So the first step is to find a vulnerability and then overflow the buffer that is vulnerable. Then the second step is to overwrite a saved return address so that when function returns, register RIP will be overwritten with the saved RIP value. And also, we want the RIP points to the shellcode. In the end, once RIP points to the shellcode, it will start to execute the shellcode, which is saved in the buffer. Given these 4 steps, can we stop the exploitation in any of those 4 steps? If we can kill the exploit in any step, then we can kill the entire exploitation process. So the question is, how to hold the stack? The first defense mechanism that I would like to discuss is stack canary. This technique brought this notation of canary and set up a canary on the stack. Stack canary is set up in each function. So at the start of each function, it will set up a randomized value on the stack, and then before the function returns, it will check this value again. In this case, if there's an overwrite happen, the overwrite will have to be equal to this randomized stack canary value. Otherwise, it will detect that the value got changed and go to stack check fail. Having the stack canary value exactly equal to the overridden value is very challenging because stack canary is 8 byte for x86-64, and also this random value is predefined per thread before the function main is called. So in order to get this random value is almost impossible. However, the lucky thing is that this randomized value is stored in stack. So we can come up with ways to bypass stack canary. In fact, to know where this randomized value coming from, we can either, in GDB, use info, oxv, or we can just read that information from the process. So if we know the process ID, we can get the byte associated with this particular field, AT_random. And usually for stack canary, the last byte of the canary will be set to be equal to 0. So here, if you check the address of this 16 random bytes, you will get the address of it, which ended with E0C9. And if you check the value that are stored in this particular address, you will find that the value over there is almost equal to the setup randomized value in stack canary, other than the last byte. So the reason why the last byte of the canary is set to be equal to 0 is because if the overwritten buffer want to overwrite stack canary and want to be equal to the stack canary, the overwritten buffer has to contain this 0 byte. However, it is known that a buffer contains 0 byte will be very unlikely because vulnerable functions such as strcpy or strcat will not allow byte 0. There are some ways that we can bypass that canary. However, there's no general approach that will work for all stack canaries. So here I will talk about 3 possible ways. The first is leak the canary value. If there is a buffer overflow, and followed by the buffer overflow, there is a read and print out, we can get the value of the stack canary using the print function and then concatenate that value with the overwritten buffer. For example, suppose that we have a vulnerable function called vul, and in that function, there's a for loop that will read buffer and then print the buffer. So if we overwrite the buffer and the lowest byte of the stack canary, when we print the buffer, we will be able to print the entire overwritten value followed by the stack canary value. In this case, we will be able to know the other 7 bytes of the stack canary. And as we always know, the last byte of the stack canary is 0. So we can put these two together and we will be able to still overwrite the buffer to the saved RIP without violating stack canary checking. Another way is to overwrite the entire predefined canary, which is stored on stack. As I mentioned, the predefined randomized value is stored in stack. So if we overwrite the buffer all the way down into the predefined canary, we can just define the canary value by ourselves and copy-paste the value onto the position of the stack that are supposed to save the stack canary in the function. So in this case, we overwrite the true value as well as the saved stack canary value. And when the stack canary check is invoked, it will consider the value as equal, and it will not call the stack canary fail checking. The last method is to hijack the stack check fail, which is the failure function when the rule is violated. However, in order to do that, we need to either change .plt session or change the got.plt table, and this may require another vulnerability, such as an arbitrary rate, which will enable us to overwrite the function of stack check fail. And here we're not really overwrite the exact function bytes inside this function. What we're overwriting is the function pointer that points to the actual stack check fail. So we can just point it to somewhere else, which will not pause the execution of the program. Okay, so the above is about stack canary. So stack canary really stops the process between step 2 and step 3. So the buffer will still overwrite the saved return address. However, stack canary will take into effect before register RIP points to the shellcode. And if stack canary is failed, then we can use our next approach called ASLR, which will stop RIP points to the shellcode property. ASLR is short for Address Space Layout Randomization. So the way that it works is that it will shuffle the address of the buffer so that when we overwrite the return value, we will not be able to localize the start of shellcode. So in this case, if the address of shellcode is randomized, we cannot point to the shellcode correctly. Unfortunately, there's also a way to bypass ASLR. One way to bypass ASLR is to leverage jump RSP. So recall that in our last week's lecture, we talked about how function return works. In short, when return instruction is called, RSP, which currently points to the saved RIP, will pop, and the pop value will be assigned to RIP. And then, after popping, RSP will move higher because the bottom of the stack got changed. And then, based on the value of RIP, it will start to execute the instructions that the current RIP points to. However, if we change the saved RIP value to the address that points to the instruction of jump star RSP, then in this case, when RIP points to the instruction and when the instruction is executed, it will then jump to the location that RSP is currently pointing to, which is still on the stack and can be controlled by an overwritten value. So in this case, if we put the shellcode after the saved RIP, and then after we call jump star RSP, it will jump to the shellcode directly. Now we're going to show you a simple demo. In this demo, we are going to keep using the vulnerability and the vulnerable code that we had before when we show the shellcode video. In addition, we add a particular instruction over here, which is jump star %RSP. And the reason why we add this is because we just want to have a way to easily locate a specific place that will be able to contain the instruction of jump star RSP. In real world, we don't really have to do that. If you learn return-oriented programming later, you will understand and be able to find such kind of quote-unquote gadget by using tools such as RP gadget so that you don't have to contain these instructions in the vulnerable code. Having this is just for an ease of demonstration. So now we have this code, and the way that I compile it is to use GCC followed by the source code and then no PIE. This is because I want to be able to locate the instruction jump star RSP in a constant way. So I just turn on no PIE, no position independent executables. And then I am going to have no stack canary because I'm not going to show stack canary for this particular demo. So I'm going to do fno stack protector. I will need the stack to be able to execute it. So I'm going to do -c exec stack and then ASLR. Okay, and now let me just open the source code again for our reference. And I'm going to show the attack code on the right-hand panel. Similar to the attack script that we have for the shellcode video, the entire input is composed of 3 parts. The first part is the padding, and here 72 is the distance between the vulnerable buffer and the saved RIP. And then we're going to put address. Instead of the address of the shellcode, here the address that I'm putting is the address of instruction jump star %RSB. And let's take a look at this. In our code, we could do opsum -d, and then we can just find this particular instruction over here in function jump. And we see that the address of it is 40057B. So we put 40057B over here, and we pack that, encode that to little endianness using struct.pat. So we put the address over here. So this will be the address that overwrite the saved RIP, and it will point to jump RSP. So after jump RSP is invoked, it will then start to execute the shellcode, which is RSP is pointing to. So in the end, we're going to just put the shellcode after the address, and the shellcode is the same shellcode that we had in the previous video. And similarly, we're going to call the vulnerable function using pom.process, and then set the string, and then interact with the process after we get the shell. I'm going to run this. And then if I do who am I, you'll be able to see the account. Or I can do ls, you'll be able to see the content in this directory. Besides stack canary and ASLR, there's another mechanism called WXORX, which is used to stop executing shellcode from buffer. WXORX is short for write XOR execute. In this defense mechanism, a memory page is either writable or executable, but not both. In Windows, it has another name called DEP, Data Execution Prevention. This is slightly different, but the high-level idea is similar. And the spirit of WXORX is also implemented in CPU. And in common CPUs, there is a particular bit called NX bit, no execute bit, so that when the no execute bit is turned on, the associated memory will no longer be able to execute it. This sounds really powerful because in this case, there's no way to execute any content in the stack because the stack will be set as only writable rather than executable. However, it turns out there are still ways to bypass WX or X. Although it is challenging, it's still doable. We will talk about this in our next video. I will create another video talking about return-oriented programming, which is an attack that will be able to bypass all the above-mentioned three techniques. And for now, let's just skip this and talk to our next topic, which is how to avoid stack overflow. Although there are defense mechanisms, there's almost always a way to bypass the defense. So for us, it's very important to avoid stack overflow when we program. To avoid that, we should pay attention to those functions that we use, especially for those that are related to string copy or memory copy. So we want to avoid insecure string copy or memory copy functions such as start copy, start cat, or get, or asprnf. Instead, we want to use start in copy, start in cat, fgets, and smprintf, which will specify the size that will copy from the source to the destination. Also, when we use map copy, we need to pay attention to the size argument. Besides using more secure functions, we also want to check the size of the source argument. Sometimes people just think that as long as there is a specified size, it will be secure, and then they just use size of source by default, which doesn't really help avoiding stack overflow. So we want to check the size, making sure that the size of the source plusing the current size of the destination will not exceed the total amount of the bytes that are allocated to the destination string or buffer. This sounds very simple, but actually there are still many stack overflow vulnerabilities that exist in the world. So let's pay attention to that when we write program by ourselves. Here I have some command tips that will help you when you analyze binaries. First is the command for checking binary security setup. The command is called checksec. If you use checksec followed by the path of the binary, you will be able to see the architecture, whether or not it is relocatable, and if there are stack canary or an X or PIE, position independent executable. ASLR is operating system setup, so it will not be able to show in a binary information. However, if the binary is not position independent, it will show that PIE is not enabled. In this case, if PIE is not enabled and if ASLR is not enabled, we will be able to know that a binary will always execute at the same address with the same stack or heap layout. Another tip is those commands that you will need if you want to compile a specific binary without a specific security mechanism. This will help you if you are going to compile those binaries and try to exploit them. If you want to turn off stack canary, you need to specify -f no -stack -protector will compile it. And if you don't specify this particular option, by default, GCC will enable stack canary. Similarly, for WX or X, you want to make sure that you have the -z exec stack command enabled. And for ASLR, as I mentioned, this is an operating system setup. And what you need to do is to put 0 into the file with the path of /proc/c/kernel/randomize va space. So the original value is 2, and you want to change that to 0. And notice that you need to have the sudo or say root privilege. In the end, if you want to turn off PIE so that when the program is running, the instructions will point to a constant place, you could use GCC with the option of -no -PIE.